In a 3D scene, the camera is the point of view of the user. It defines what we see on the screen. We don't have to restrict ourselves using only one type of camera and using only one single camera at a time. For example, if you take like split-screen games, you have multiple cameras rendering the same scene from different point of views. You can also have your main camera following your character, and on the bottom of your screen you will have another camera rendering the scene from the top view, and it will be your minimap. With Three.js, there are different types of cameras available. We will see three of them: the perspective, the orthographic, and the cube camera. Before diving into the different types of camera, we will discover what is Orbit Controls. Let's start by downloading the starter project, run yarn to install the dependencies, and run yarn dev to start the development server. We have that low poly version of Rio de Janeiro. We have our camera position at this static place and we can't move around. To be able to move and rotate inside the 3D scene, we can use a component named Orbit Controls. It's from Dry Library. You can see the import here. You can use Control Space to do the auto import if it's not the case when you hit enter. Now we are able to move our camera position. We can click and drag to move around the camera. We can use the mouse wheel to zoom in or out. And we can use the right click or shift and drag to pan the cameras around. It's also compatible with touch devices like smartphone and tablets. For now, it's all you have to remember about Orbit Controls. We will dive deeper into this in the controls lesson. Let's talk about perspective camera. This is the default camera that we have when we set a canvas with React 3 Fiber. We can change its property with the camera prop and setting the different in this object. For example, we have now the position, which is the default position. We can use comma and see the other props we can attach to our camera. But we can also define camera another way. Instead of doing this, we can declare a perspective camera and use the props like we do for any other component. For example, position, we will say 0, 8, 0. So we put our camera on top of the stage. And to tell Three.js that it is our main camera, we can use make default. By the way, when we use a prop like this without any value, this is because it is a boolean, so by default it will apply true. It's the same than doing this, but I don't need to do this. Now, if we reload our scene, we can see we are on top of Rio de Janeiro. We can change other parameters on our camera, for example, the field of view. It's named FOV, and it's the angle between the top and the bottom. The default value is 75 degrees, so if we decrease it a lot, and let's also reset our camera position to 3, 3, 3. We now see less of the scene and it's like we are zooming in. On the opposite, if we say 130, it appears very deformed, but we see all of the scene without zooming out. Another useful prop for our camera is the aspect ratio. Let's remove the field of view and use aspect. Let's put it to 1. And by default, it's calculated automatically by React 3 Fiber, and it's using the width and height of the screen. If we want to force it to 1, we have to set manual. An aspect of 1 means we have the same width and height on our screen, so it should be displayed in a square. But because our screen is not a square, we can see that the scene looked like it's stretched. Most of the time you can use the default value, so we can remove it. Let's talk about the near and far properties. Their default values are 0.1, and the far property is 1000. It defines the range that the camera will display on screen. So from 0.1, so everything below that won't be rendered, and everything further 1000 won't be rendered. In some video games, you might have noticed that effect when you see trees appearing from very far, or if you can see through wall when you get very close to it. To better understand what it means, let's change the value. For example, let's say near 5 and far 8. Now we can see our city is truncated because everything before 5 is not rendered and everything further away from 8 is also not rendered. You can use the orbit control to see that it's not the city who are not rendered, it's really based on our camera position and the distance between it. You might need to alter this property from some rendering effects, but also for performance optimization. Let's talk about the second type of camera, the orthographic one. While the perspective camera is closer to what our eyes see in the real life. The orthographic one has no perspective, so wherever you look at, the objects appear in the same dimension. This is often used in some type of game like Warcraft 3 or Roller Coaster Tycoon. Let's change our camera to an orthographic one. We remove the near and far properties. And we can set the position to 1, 1, and 1. Now our city appears very far. We need to zoom in a lot. We have different solutions to see it better. Using the zoom property from the orthographic camera, we can say 100. Now without zooming, we can see our city. You can see that it is truncated here and that the rendering is different than when we were using the perspective camera. It is because now we have an isometric view. But instead of using the zoom property to define our field of view, we can use the top, left, right, and bottom properties. So we can say precisely what we want to render. So let's say top is equal to 2, bottom to -2, left will be -2, and right will be 2. Now our image looks stretched because our field of view is a square and we are not using the aspect ratio. Because we are setting the field of view manually doing this, let's multiply it by the aspect ratio. So on the side, like we said earlier, we will use window.inner width to have the width of the screen and inner height to get the height of the screen. We do the same for the right property. Now it looks a bit better, but if you look closely to the bottom right here, we have something called clipping issue. This is because the city and our camera are too close, so we need to adjust the near property. For example, we can put it to -5. Now we can perfectly see our city in isometric view thanks to our orthographic camera. The trees very close to us are the same dimension that the trees very far on the rock there. I guess it is trees. The last type of camera that we will cover in this course is the cube camera. This is a camera that renders our scene 6 times for each side of a cube. It's often used to create environment maps or lighting effects. But this is a more advanced topic that we will cover in the staging lesson.